Good morning, students. As per request of most of the students, I wanted to discuss bridge bonding. तो ब्रिज बॉन्डिंग केमिकल बॉन्डिंग का एक इम्पोर्टेंट हिस्सा है, तो उसके बारे में मैं आज डिस्कस करने जाऊंगा। उसमें ब्रिज बॉन्डिंग ऑफ BH3 मॉलिक्यूल। तो BH3 मॉलिक्यूल एग्जिस्ट इन टर्म्स ऑफ डाइमर, दैट इज B2H6, विच इज नोन एज डाइबोरेन। इसका नाम हम लोग बोलते हैं डाइबोरेन। ओके, so what is structure, shape, hybridization, how the bond is formed, and some properties of B2H6 molecules we'll discuss on today's lecture. At ordinary temperature, our BH3 boron hydride undergoes dimerization very easily, and due to this readily dimerization, we can write this equation 2BH3 giving you B2H6 diboron. Diboron is a poisonous gas and it is highly reactive, and the driving force for the dimerization reaction is that is momentarily the octet of boron atom in B2CH6 and the hybridization structure of B2H6. This reaction proof can be given whether this equilibrium exists between monomer of BH3 and dimer of BH3 is there or not, can be seen by the following reaction. Suppose you take B2H6 and you dissolve with cyclic ether. So this is known as tetrahydrofuran, THF. This is a cyclic ether. If you give this, then you will get like this BH3. This is 2 number of this. So this becomes donor, this becomes acceptor. How this reaction takes place? Oxygen containing lone pair can act as donor to diboron. So in diboron, suppose you break diboron into BH3, 2BH3. So in BH3 it is incomplete octet. So it is incomplete octet. So if oxygen atom makes coordinate bond with boron and acting as donor and boron becomes acceptor, so there is a coordinate bond like this. Coordinate bond like this, BH3. Okay. Then octet completion of boron will be there. So here oxygen will act as donor and boron will act as acceptor. This is the coordinate bond. And you know that coordinate bond can be written as single covalent bond by making donor atom plus, acceptor atom minus. So this shows that diboron and monomer of diboron BH3 exist in equilibrium. Okay, then what is the hybridization shape structure of B2H6? So in order to understand this, so many experiments have been done. So one more reactions I can highlight. So in diboron, say B2H6, when it is reacted with dimethyl sulfate CH3 2SO4. Okay. So dimethyl sulfate if you give, then it is found that you are getting CH3 four times. Okay, CH3 four times and B2H2 plus. So if this is four times, this must be 2 in order to balance. So 2 sulfate coming. So from here H6 2 left. So you have 4 hydrogen. So if you make 2H2SO4, then 2 sulfate, 2 sulfate, 4 hydrogen balance. So this is the reaction. So in this reaction, what you find? You find CH3, 4 molecule of CH3 replacing 4 hydrogen atoms. Okay. So out of 6 hydrogen, you see in diborane you will find 6 hydrogen atom. But out of 6 hydrogen atom, you will get only 2 hydrogen atom left. So 4 hydrogen atoms are replaced by CH3. And this type of reaction is known as methylation reaction. Methylation. Methylation means methylation means methyl group CH3 group replacing, this replaces hydrogen. So CH3 group replaces hydrogen, but you find that 4 CH3 group replacing 4 hydrogen from the diborane. Out of 6 hydrogen, only 4 hydrogen replaced and 2 are not replaced. So that means in diborane, the structure of diborane should be like this. So 4 hydrogen should be of one kind and 2 hydrogen should be of another kind, a different kind. So 4 hydrogen one type and 2 hydrogen should be another. So when the X-ray diffraction is done, it shows that in diborane, it, it is found that in diborane the bond length of BH bond length. Okay, so BH bonds are two types. One bond length is coming to be 1.33 angstrom and another bond length is coming to be 1.19 angstrom. So only two type of BH bonds are there. One is shorter bond, another is longer bond. This is shorter and this is longer bond. So that means, so 4 hydrogen of one kind and 2 hydrogen of another kind. Out of 4 hydrogen, either 4 hydrogen boron must be longer and 2 hydrogen out of 2 hydrogen that might be longer or shorter. We don't know what should be the hybridization. Now let us try to draw the structure of BS3. BS3, we can draw the structure of BS3. Lewis structure of BS3 is like this. You have studied in valency bond theory. Boron is having valency shell. Let us see the configuration of boron. Atomic number 5, 1s2, 2s2, 2p1. But it is making 3 bonds with 3 hydrogen. So 3 sigma bonds say it is making. If it is making 3 sigma bond, then you studied that in valency bond theory, number of bonds is equal to number of unpaired electrons at the central atom must be there. But we have not taken 2py and 2pz, 2py0, 2pz0. But in ground state it will not form bond. So in excited state of boron atom, one electron will jump from 2s to 2py. To 2pz is vacant. So now you got 3 unpaired electrons. So suppose you got 3 unpaired electrons, then in BH3 the hybridization should be sp2 hybridization. So due to sp2 hybridization, you will get 3 sp2 hybrid orbital. So in boron, you will get sp2 hybrid orbital, sp2 hybrid orbital, sp2 hybrid orbital. So this is sp2, sp2, sp2 of boron. Then hydrogen will overlap one hydrogen, 1s of hydrogen, 1s of hydrogen, 1s of hydrogen. This is the structure of BS3, monomer of diboron or boron hydride. So, okay, this structure is understood, accepted. Hybridization is sp2. But what is the hybridization of B2S6 and structure of B2S6? Now, BH3 is making this structure. Okay, this is BH3. Let us write. Let us write again BH3 like this. But B2H6 exists. If B2H6 exists, and what there must be bonding between boron and boron. Now boron bonding, how possible? In boron, due to 1s overlapping of 2s, 1s overlapping of 2s, 1s overlapping of 2s, these electrons are paired. These electrons are paired. These electrons are paired. So there is no electrons which are unpaired. Neither there is no lone pair. On contrary, 2p is having vacant orbital 2pz0. So how boron and boron bonding takes place, or boron hydrogen bonding takes place? So this was mystery till 1923, before Dilthey discovered a new type of bonding. In 1923, Dilthey discovered a new type of bonding for diboron, and that new type of bonding is what? Let us see. Let's go to next page. So new type of bonding in diboron is assumed by Dilthey, and he told that let us take the electronic configuration of boron. Then we can understand. In boron we have 1s2, 2s1, 2px1, 2py1, 2pz0. This is the electronic configuration in excited state of boron. So 1s2 is inner cells, 2s is outer cell, 2px, 2py and 2pz are outer cell. So in order to understand the bonding in BH3 and BH3, what should be bonding? So it is assumed that there might be some vacant orbital in boron and some electron in hydrogen will help the formation of bond. So let us see in the next page, we will check how the bonding is there. Okay. So now see the bonding for this. It is assumed by Dilthey that there will be sp3 hybridization. Instead of sp2 hybridization in BH3, there will be sp3 hybridization. Let us make sp3 hybridization. Okay. sp3 hybridization. Okay. So if sp3 hybridization is there, then there is a vacant orbital. Yes, in valence bond theory, in one statement it is written that vacant orbital also take part in hybridization, lone pair also take part in hybridization, unpaired electron also can take part in hybridization. So here vacant orbital takes part in hybridization. So if all these S and Px, Py, Pz will intermix, then there will be sp3 hybridization. So sp3 hybridization means there will be sp3 hybrid orbital according to valence bond theory, hybridization theory. So sp3 hybridization, sp3 hybrid orbital, sp3 hybrid orbital, and sp3 hybrid orbital. So you will get sp3 hybrid orbital. So due to sp3 hybrid orbital, there will be only 3 electrons but 4 hybrid orbital. So how to distribute these electrons? We can distribute these electrons like this, like this, like this, and one is vacant. Okay. So this is status of boron, hybridization of boron. Again, let us take one more boron. Okay. So in another boron also similar phenomenon occurs. Here 1s2 and you will have let us write boron here. So I will use eraser sharp. Let us write boron here. Okay. So in boron you have 1s2 again, and again you can have, sorry, you can have like this 2s1. This is 1s2, this is 2s1. Okay. You can have sharpener, eraser again. Okay. Then after that we can have 2px, 2py, 2pz. So this is 2px, 2px say 1 electron, 2py 1 electron, and 2pz is vacant. So 2px, 2py, 2pz. So it is told that there will be hybridization sp3. Okay, let us make hybridization sp3. In another boron also similar phenomenon sp3 hybridization. Due to sp3 hybridization, there will be 4 hybrid orbital sp3, 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 sp3. So you will get sp3, 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 sp3 of boron. So 4 hybrid orbital will be formed. So we will have electrons. This is one electron, this is another, this is another. So one sp3 hybrid orbital is vacant. So in boron this will happen. So if this will happen in boron, then let us draw the orbital diagram of two boron. One boron is here sp3 hybridization. Okay. Another is sp3 hybridization. Another is sp3 hybridization. And one more is sp3 hybridization. So assume that these are sp3, 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 sp3. This is for boron. Okay. So one more boron also you have to take. So one more boron also similar type hybridization also there. So let us make hybridization here. This is sp3. This is sp3. This is sp3. Again sp3. So assume sp3, sp3, sp3. Don't go through the shape. sp3 hybrid orbital means there should be tetrahedral shape like that. Don't go by that shape. We are seeing the hybridization. So we can view in different way. It looks different. Suppose it is tetrahedral. You are seeing from another view. It may look like this also. So this is boron. Okay, sp3 hybridization. But thing is that in boron sp3 hybridization we will have all hybrid orbitals 4 but 3 electrons are distributed. यहाँ पे देखो 1 2 3, ये देखो 1 2 3. So 3 electrons are distributed. Let us distribute the electrons also. Okay, so electrons will distribute 1 2 3. So this is vacant. 1 sp3 is vacant, right? So again here also you distribute 1 2 3. Let us make this vacant. So boron are there. sp3 hybridization like this possible. Now we have 6 hydrogen atoms. So how to write, how to arrange these 6 hydrogen atoms, how to make bonding of 6 hydrogen atoms. We studied that 4 hydrogen atoms of one kind and 2 hydrogen atom of another kind. From where we studied? See, we have studied from here when it is undergoing what? When it is undergoing methylation reaction. Then you found that 4 hydrogen atoms are replaced by CH3 group. Means 4 hydrogens are one kind and 2 hydrogens are not replaced. Means 2 hydrogens should be of another kind. Okay. So next, let us go to the next page. Okay. So here, 4 hydrogen one kind means, so we can think that 4 hydrogen must be a terminal hydrogen. 4 hydrogen terminal hydrogen. Let us take boron here. Boron here. Let us try to draw the Lewis structure. So 4 hydrogen of one kind. Let us make 4 hydrogen this side. So terminal hydrogen. Make a single bond. Okay. Make a single bond. So 4 hydrogens are terminal hydrogen. So they are making bond with boron, and 2 hydrogen where it will be there we don't know. So let us keep 2 hydrogen at the middle here and here. Okay. So how the bonding will be there? Now let us see. So 4 hydrogen terminal means they can make single bond with boron. So single bond with boron means that single bond must be what type of bond? Sigma bond. So sigma bond, sigma bond, sigma bond, sigma bond with hydrogen. And this 2 hydrogen, how it will be bonded, we'll check. We'll see. Okay. So let us complete because these 4 hydrogens are one kind. So they are replaced by methyl group. Okay. And bond length are two, one is longer, one is shorter. We don't know which is longer, which is shorter. So we will check later on at the ending part. Now 4 hydrogens, suppose we take hydrogen atom here, say hydrogen atom, let us take hydrogen atom in blue color. So we take hydrogen atom here. This is one hydrogen atom. So it will be like this. This is one hydrogen atom. This will be like this. So this is hydrogen atom. This is hydrogen atom. So this is sp3s overlapping with this hydrogen, sp3s. So this side also hydrogen atom is there. This hydrogen atom let us make like this, and one more hydrogen atom let us make like this. So unpaired electron becomes paired. We are applying valence bond theory. So hydrogen is making sigma bond, sigma bond, sigma bond, sigma bond. 4 sigma bond like this. So 4 hydrogen of one kind we got. So 2 hydrogen of another kind. How that will be there? So if we take hydrogen, one more hydrogen in middle. So if we keep that hydrogen can form bond with this side, this. Then how this will be bonded? And suppose we keep one more hydrogen here, that hydrogen will make bond with this. But then this will be BH3 separated, this BH3 separated. Okay. But B2S6 exists. So how B2S6 exists? Suppose we will make hydrogen here. Suppose our hydrogen is here. Okay. And this hydrogen makes bond simultaneously with this boron and this boron. So if this hydrogen is making simultaneous bond with this boron and this boron, okay, then suppose this is the hydrogen, this is the electron. It is making bond simultaneously with this boron and this boron. Then only this dimer of BH3, that is B2S6, exists. So we think that this hydrogen sharing its electron, and already we have one electron, but it is making simultaneously bond with this boron and this boron. Similarly, here also one more hydrogen, okay, is making bond simultaneously with this boron atom and this boron atom, and it is sharing one electron. Okay, it is sharing one electron, true. But when covalent bond is formed by mutual sharing of one electron each, by two atoms, single bond is formed. So this side BH single bond form is understood. But how this also makes bond with this? So this makes bond with this. Strange. Is it possible? So we studied that in H will share one electron, another H will share one electron. So bond is formed. Suppose Cl and H. Cl will share one electron and this H will share one electron. So HCl single bond is formed. So if H is sharing one electron, this boron is sharing one electron, between BH bond is formed. And similarly BH, this bond is formed. So BH3 bond is there, BH3 is there, but how both will be connected? So here both will be connected. This is strange. This is a new type of bonding, and this is discovered by Dilthey in 1923. And this bonding is that it will share one electron, and in sp3 hybrid orbital also one electron. But this sp3 hybrid orbital does not have any electron vacant orbital. That means two electron, but this boron, this hydrogen, this boron. So three atoms are involved in bonding. Means this is what system? This is two electron, three center system. This is a new type of bonding. Remember, please remember, this is very important for JEE mains and JEE advanced for NEET exam. Two electron and three center. Two electron and three center bonding will be there between this boron, this hydrogen, and this hydrogen. This bonding will be there. Here also, this hydrogen sharing one electron, this sp3 hybrid orbital sharing one electron. So two electrons coming, but the bond will be between boron, hydrogen, and boron. So this bond is known as two electron, three center bonding. Okay, this is a new type of bonding. This is not explained by valency bond theory, a new type of bonding, and that bonding is two electron, three center system. But in all these type of bonding, what we studied in valency bond theory is two electron, two center system. So here it is sharing one electron, H is sharing one electron, so two electrons are shared between two atoms. So two electron, two center system. But here it is possible that two electron, three center system in diboron. So if H is making simultaneous bonding with B and B, we can write like this. We will connect here. Okay. So H is making bridge between two boron atom. This H is also making bridge between two boron atom. So this is known as bridged bond. Okay, this is known as bridged bond, and this type of bonding is known as bridged bonding. Okay, so we got two type of bond length, 1.33 angstrom and 1.49 angstrom. Okay. So we got two type of bond. One is shorter, one is longer. So out of these, which should be shorter bond, which should be longer bond? See, this type of two electron three center is a new type of bonding. Here, three atoms are coming within two electrons. So the overlapping will not be effective overlapping. And here the bond length won't be small. Here bond length should be big. So this bridged bond, these are bridged bond, and bridged bond BH bond length should be the bigger one. So this is 1.49 angstrom, okay, and this should be 1.33 angstrom. So this should be shorter bond, this should be longer bond. Why? Because this is making bridge between these two boron, which is not easy. So here the bond will be longer. So okay, that is understood. So this is making a bridge bond. But question arises: are all BH bonds are in same planar? So whether it is planar? No, it is not planar. Since it is sp3 hybridization, all sp3 hybrid orbital cannot lie in the same plane. If all sp3 hybrid orbital cannot lie in the same plane, then definitely two bonds will be out of plane. So around this boron atom, suppose these two bonds we keep in one plane, that is on the plane of this blackboard, then these two bond cannot be in the same plane as that of this green bond plane. This see parrot green bond plane and this purple color bond plane cannot be in the same plane because this is sp3 hybridization. sp3 hybrid orbitals are not planar. So how the bond will be there, how they lie in three-dimensional space. Suppose if we take this boron, okay. Suppose we take same color, right? Suppose we are taking same color. Suppose this boron is here, this boron is here. Here we got hydrogen, here we got hydrogen, right? And again we get this hydrogen and side hydrogen. These are called terminal hydrogen. These two are called bridged hydrogen. These two are called bridged hydrogen, and these four are called terminal hydrogen. Okay, so this is called terminal hydrogen. Terminal hydrogen. And this is called bridged hydrogen. So bridged bond, so this hydrogen is called bridged hydrogen. Bridged hydrogen. Right. Now we have these purple color bonds, and we'll have this parrot green color bond. Suppose we keep this parrot green color bond on the plane of blackboard, then these two will not be on the same plane. If it is not on the same plane, we can keep this purple color bond above the plane of this green bonds or blackboard plane and below the plane. Suppose we keep above the plane and below the plane, that we can show like this. We can show like this. Suppose this is above the plane, we can show by thick line. So this is above. This color is very bright color. We can take some light color. Okay. So let us take some light color so that it looks clear. Okay. So this blue color is above the plane, and this will be below the plane, because these two plane cannot be same plane of these two, because these two plane we kept in the on the plane of blackboard. Any two bond out of four in sp3 hybrid orbital can be kept in one plane. If these two bonds are kept in one plane, these two bond cannot be in the same plane as that of this green bond plane. So here we can keep this edge below the plane. So below the plane in wedge dash projection, we write like broken line like this. So this is wedge, this is dash. So this is below the plane. This is above the plane, and this is becoming below the plane. Okay. Similar fat will be for these two terminal hydrogen also. This will be below the plane. I'm showing sky blue color, and this bond will be above the plane that I am showing with ocean blue color. See, this is ocean blue color. Okay, this is above the plane, this is below the plane. Okay, and this looks like two bonds are approaching towards you, two are away from you, and these two bonds are on the same plane of parallel to you. Okay, so this can be uh, thought of making bond like this. So here two hydrogens are here, and here two hydrogens are here. Here hydrogen is making bond. One is above the plane like this, one is below the plane like this, and one is above the plane like this, and one is below the plane like this. So these are four hydrogen, and these are two bridged hydrogen, and it looks like banana. This is also called banana bond, and this is called bridged bond. So this is structure of diboron. Now this overlapping is your sp3 s overlapping. This is also this BH bond is sp3s overlapping. This is sp3s. This is also sp3 of boron and s overlapping. But this is 2 electron 3 center system. The question will come, how many 2 electron 3 center system in diboron? So what is answer? Yes, it will be 2 here and here. Okay. And how many terminal hydrogen? 4 terminal hydrogen. This is structure of diboron. I think it is Now very much clear about hybridization structure of diborane. So like diborane, we can discuss some more molecules forming this type of bridge bonding. So for that, let us go to the next page. So we have seen BH2, beryllium hydride. BH2, let us take BH2. Okay. So beryllium hydride, suppose you take beryllium hydride hybridization, if you see, it will be sp. You are already studied in valence bond theory, and it is making two sigma bond with two hydrogen atoms, sp hybridization. But it is found that BH2 twice, that is B2H4 exists, and it is found that BH2N also exists. It exists in polymer. Here it exists in dimer. So first let us see the structure of dimer. Then we will discuss about structure of polymer. That is B2H4. Suppose you have BH2. Okay. Beryllium dihydride. Another beryllium dihydride. Let us make beryllium dihydride like this. So one beryllium dihydride we made like this. Another beryllium dihydride also we made like this. Okay. So now let us clearly draw beryllium hydride. We thought this is sp hybridization. It should be linear shape. Let us make it linear. Otherwise, what is that? Okay. So now BH2. But how the bond between these BH2 BH2 will be formed? The bond between BH2 BH2 will be formed. So suppose this is a bond pair. This is also bond pair. Now this bond pair containing two electrons can form bond with vacant orbital of beryllium, just like diborane. So here also these two electrons bond pair will make bond with vacant orbital of beryllium. So these two electrons will form bond between beryllium, hydrogen, and beryllium. So beryllium, hydrogen, beryllium, beryllium, hydrogen, beryllium means you will get beryllium, hydrogen, beryllium, and here also you will get beryllium, hydrogen, beryllium, and these two hydrogens. Now we are not seeing the three-dimensional structure. We are first establishing the bonding. After that, we'll take three-dimensional structures. Now, beryllium. Let us see. Beryllium was making sp2 hybridization. Beryllium is atomic number 4. So, 1s2, 2s2 configuration. But in excited state, beryllium will be changing to what? 1s2, 2s1, 2px1, 2pj y0 and 2pz0. So many vacant. Py vacant, pz vacant. In boron, so only pz was vacant. So many vacant orbital, two vacant orbitals. So it was making sp hybridization. In the same way, like B2H6 will include one more p orbital. So the hybridization will change from sp to sp2, sp1 to sp2. Okay. So suppose the hybridization is sp2, then you will get sp2, sp2, sp2 hybrid orbital. But you have only two electrons, so one vacant hybrid orbital will be there. Okay, and 2pz is also vacant, no problem. So in beryllium this will happen. So beryllium hybridization will change from sp to sp2 to sp2 hybridization. Okay. So if beryllium is making sp2 hybridization, let us draw the shape of sp2 hybridization. So sp2 will be what geometry? It is trigonal planar geometry. Okay, right. So we'll make trigonal planar geometry only like this. trigonal. So beryllium, but we have only two electrons. Okay, so we have two electrons, and it is beryllium. We have two electrons. Now this is uh, not looking good. Let us rotate it. Okay. Let us write in proper orientation so that bonding will be easier. Let us write here. So here electron is coming. So this is beryllium. This is another beryllium. So we have only two electrons for three hybrid orbital. Yes, beryllium. So we have two electrons. So this beryllium also sp2 hybridization. This beryllium also sp2 hybridization. Just similar way of hybridization and bonding of diboron B2S6. Okay. Now this beryllium is making bond with hydrogen. So okay. So let us take bond with hydrogen. This is hydrogen. Sigma bond with hydrogen. Okay. So this beryllium also make sigma bond with hydrogen, right? So this beryllium is making sigma bond with hydrogen. This one and this one. But these two are involved in forming a new type of bonding, that is two electron three center system. Okay. Now your hydrogen will come. Suppose your hydrogen is coming here. Hydrogen is coming here. Okay. So hydrogen is bringing one more electron. So these electron, two electrons are forming bond with beryllium, hydrogen, beryllium. Means two electron, beryllium, hydrogen, beryllium, three center. So two electron, three center. Similarly, here also we will make hydrogen and electron. So these two electrons, here it is vacant, here one electron, here one electron. So two electrons of hydrogen and beryllium is making bond with beryllium, hydrogen, beryllium. So this is also two electron, three center. Okay. So fortunately, here you need not to worry about the orientation and the bond plane lying, because all sp2 hybrid orbitals are planar. So all are planar. So all will stay in the same plane because they are planar. Okay. So whatever. So here hydrogen bonding is there. So you will get uh, two terminal hydrogen. Okay. And acha, here I have done some mistake. Here terminally there was one hydrogen. I have taken two hydrogen. Let us clean that. Okay. So here this will not be there. And here the terminal only one hydrogen is there. So this is not there. Right. So now this is the orbital diagram of your dimer of beryllium hydride. So this diagram is there, and these are two electron three center, and these are terminal hydrogen. So this is structure of BH2. Okay. If this is structure of BH2, then what will be the structure of polymer of BH2? So let's go to next page. So polymer of BH2. Now let us take BH2. BH2. Okay. So you take one more BH2. BH2. You take one more BH2. Like this, you keep on taking till n completes. So if you take like this, it is continued. It is continued. So now these two electrons between BH bond and these two electrons of BH bond, these two electrons of BH bond and these two electrons of BH bond. So these two electrons of BH bond form two electron three center bonding with this beryllium, including this beryllium. So this will include this beryllium. This will include this beryllium. This will include next beryllium, and so on. And two electrons will come from these two beryllium. So in this way, the bond will be continued. Okay. So if bond is continued, so you will get bonding like this. Okay. So you will get beryllium here, H, H, beryllium. Okay. So again H, beryllium, again H, continue. Okay. So this will be continued. This will be continued, and but at the terminal, that beryllium will have only one hydrogen. This is the terminal. So this is structure of BH2N, polymeric form of beryllium hydride. And this will be planar. Why? Because sp2 hybridization. All beryllium is sp2 hybridization. Okay, but you will have two electron three center system for all bridge hydrogen, right? Similarly, bonding of BeCl2 in dimer, that is B2Cl4. The same manner, instead of hydrogen, you can put chlorine atom. Okay, so beryllium chlorine atom. So now bond pair between beryllium and chlorine. Bond pair between beryllium and chlorine. Here one thing, uh, there will be bridge bonding. This hydrogen also involved in bonding. So there was some mistake I want to correct. Uh, Please check this one. So here the bonding will be like this. See, so these two electrons will make bonding with this, right? Now these two electrons will make bonding with this, and these two electrons will make bonding with this. Now these two electrons will make bonding with this, already we have discussed, and these two will make bonding with this. This is wrong. This is already done. So one you have to clear. So here, if it is polymer, suppose it is polymer, then what will happen? All hydrogen will be bridge bonding. These hydrogen will be involved in bridge bonding. See, these all hydrogen. Only the last and first hydrogen. The terminal hydrogen will not be involved in bonding. The terminal hydrogen will be like this. Otherwise, all hydrogen will be involved in bonding. This will come here and this will go there. This will come here, this will go there. This will come here, this will go there. And all will make two electron three center system. Okay. Now in BeCl2, you have like this. So these two electrons can make two electron three center system with this beryllium. And these two electron also will make two electron three center with this beryllium. So this will give you Cl, single bond beryllium, and chlorine and beryllium, and again this chlorine will make three center 2 electron. So this is 2 electron 3 center. This is 2 electron 3 center, and this side 1 chlorine. But this chlorine is 2 electron 2 center. Why? Because this is sharing 1 electron, this is also sharing 1. This side also 2 electron 3 center. Okay. Now let us see the bridge bonding for the dimer of AlCl3. So AlCl3 dimer means Al2 Cl6. Okay. Now see the bonding of Al2Cl6. Now AlCl3 in aluminium, what is the hybridization? Let us check. Aluminium is 13 atomic number, 1s2, 2s2, 2p6, 3s2, so 10 to 3p1. Okay. So for forming covalent bond with chlorine, Lewis structure of LCl3 is like this. Cl makes single bond like this. Okay, this is LCl3. So means Al is making 3 sigma bond. So 3 unpaired electron is required. So in aluminium, see, its configuration will change, and it will change to like this. From 3s, 1 electron will jump to 3py. So 3s1, 3px1, 3pz, 3py1, and 3pz0. So for 3 sigma bond, 3 hybrid orbitals required. Okay. In valency bond theory you studied 6 hybrid orbitals, 3 hybrid orbitals. So in order to make 3 hybrid orbitals, so 3 hybridizing orbitals will take part in hybridization. So you will get sp2 hybridization, sp2 hybridization, sp2 hybridization. So sp2 hybridization for aluminum, then chlorine 2p, unpaired electron of 2p will overlap with chlorine. So 2p of chlorine will overlap. Next, 2p of chlorine will overlap. Next, 2p of chlorine will overlap, making sigma bond. So this is AlCl3 structures. So hybridization is sp2. Now AlCl3 is sp2 hybridization. AlCl3. Okay. One more AlCl3 also sp2 hybridization. Okay. But we studied that dimer of AlCl3 exists, means Al2CL3. Between LCl3 and LCl3, how bonding will be there? You see, this chlorine is having lone pair. This chlorine is having lone pair. And in aluminium, you see, aluminium valence shell contains 3 electron. And if it is making 3 sigma bond, it gains 3 electron. So it is getting 6 electron. So it is incomplete octet. So it is incomplete octet, so it will be less stable. So in order to attain octet, so it wants a coordinate bond from some donor atom, because in aluminium you have vacant p orbital, vacant p orbital. देखो एल्यूमिनियम में वैकेंट पी ऑर्बिटल है, तो इनकम्प्लीट ऑक्टेट है। अगर पी में 2 इलेक्ट्रॉन आ गया तो इसका ऑक्टेट कंप्लीट होगा। तो वैकेंट ऑर्बिटल ऑफ एल्यूमिनियम हाउ विल बी overlapped. So here aluminium can donate its electron and forming coordinate bond with, sorry, chlorine can donate electron and forming coordinate bond with aluminium. So this can donate electron pair. So this can donate its electron pair. So this bond can be written like this: Al, Cl, Cl. This Cl covalent bond now coordinate bond with aluminum. Okay, and this chlorine, this chlorine. So this will make coordinate bond with this aluminum. So if it is making coordinate bond with this aluminum, so it is using its electron pair, lone pair. Okay. Now see, these electron pairs are like this, and two are used, and this is having two pair, and one pair is used for aluminum. So one pair is used for bonding with aluminum, that is coordinate bond. This becomes donor, this becomes acceptor. In this case also, this becomes donor, this becomes acceptor. So here also you get bridged bonding. Okay. In this bridge bonding, you are getting coordinate bond. There is a bridge, but these two electrons are used for coordinate bond. Also, the bond pair of between aluminum and chlorine are also involved in this bridge. That means these two electrons between aluminum and chlorine and the coordinate pair of chlorine. So these two, you got four electrons involved. So when this type of bridge is formed between aluminum, chlorine and aluminum, we say four electrons are involved in this bonding. So this is four electron, three center system. So this side also, this coordinate bond is involved between this chlorine and aluminum for completing octet, because it was six electron. This was six electron due to this coordinate bond. It becomes eight electron. It becomes eight electron. And these two electrons are involved for coordinate bond, and two bond pair, that is between aluminum and chlorine, also involved in forming this bond. So total four electrons are involved, so three center. So this becomes four electron, three center system. Then what will be the hybridization? The hybridization was sp2. So we studied that there will be one extension of hybridization. In B2S6, we saw that in BS3 the hybridization was sp2, and in B2S6 the hybridization become sp3. And we saw that in beryllium hydride the hybridization was sp, and when it is making dimer B2H4 the hybridization become sp2. So here also the hybridization was sp2, but when it is making bridge bonding, the hybridization will increase and it will become sp3, and this will become sp3. So sp2 and one more p will be involved, that is pz. So in sp3 hybrid orbital, sp3 hybrid orbital, sp3 hybrid orbital, sp3 hybrid orbital, so you will have electrons. Okay, and one was vacant. Okay, one was vacant. So this vacant orbital will be coordinate bond by chlorine. So chlorine will make coordinate bond to the vacant orbital with sp3, and also these electrons are involved. So this is the bridge bonding, but you remember here the four electron and three center system will come, and the hybridization will be sp3. sp3. And this will become non-planar, and this will become non-planar. Why? Because of hybridization of sp3. Initially it was sp2 hybridization, it was planar, square planar geometry, but when it is making dimer, it becomes sp3 hybridization, so it will be non-planar. So that's all for today. I hope you enjoyed this video, and this will help you to understand the bridge bonding. Though you will study the bridge bonding in boron family, boron, aluminum, gallium, indium, thallium, in that family you will study again. But some introductory idea is required in chemical bonding chapter. So thank you and have a good day. Bye.